Okay, so last time we were discussing this thing called the monotone convergence theorem that tells us when a monotone sequence converges. Okay, and it tells us that every bounded monotone sequence, so by monotone we mean either increasing or decreasing. So any monotone sequence of real numbers is convergent. So if we want to show a sequence is convergent using this theorem, what we need to do is show these two conditions. It is bounded and it is either increasing or decreasing. So we're going to go through some examples, and there are more examples of this in the practice sheet and in the previous coursework exams you will look at. Okay, so suppose I have the sequence xn and it's given by this recursive relation. So this is what is called a recursive relation. Okay, it means that you're given the first term and you're given a recipe to find all the successive terms. So the n+1 term is the square root of the previous term and you add 1 to it. So if we want to show that this sequence is convergent using monotone convergence theorem, what we need to do is figure out what is a bound for it. And usually we would give you the bound as part of a hint because we don't expect you all to know what the bounds for the sequence might be offhand. So usually we will give it in the form of a hint. And you're given it here that the sequence lies between 2 and 3. Okay, well, this is your hint. You need to prove this. And if we don't tell you whether or not the sequence is increasing or decreasing, all you have to do, that's easy to figure out, just work out, you know what x1 is, just work out what x2 is or x3 is, and see whether or not these numbers are getting bigger or smaller. Okay, and that will hint to you whether or not it's increasing or it's decreasing. So to prove that the sequence is bounded and monotone, the proofs are usually done using induction. Okay, so we're back to this induction stuff. So if you want to show the sequence is bounded between 2 and 3, so we first need to show that the case holds for n equal to 1. So when n is equal to 1, x1, you're given that to be 2. Okay, you're given that to be 2, and clearly 2 is larger than or equal to 2, and it's certainly less than 3. So my case for n equal 1 is good. Then I need to assume that the result is true for some natural number k. So I assume that this is true for some natural number k. Okay, and then the next thing is to show that it is true for k plus 1. So consider x to the k plus 1. Oh, sorry, x k plus 1, the k plus 1 term. Well, from the recursive relation, we know that that's the square root of the previous term plus 1. And we know that, so now we need to use our inductive hypothesis. So what could we take away from this? We know xk is bigger than or equal to 2 from this. So if I square root both of these numbers, okay, then I get this. And if I add 1 on both sides, so you see what we're doing here is we're basically trying to build, we're trying to build this guy here, which is xk plus 1. So from this, we get xk plus 1 is larger than or equal to root 2 plus 1. Okay, to root 2 plus 1. And when you punch this into your calculator, you can see that this is bigger than 2. Okay, so what we learned from this first part is that xk plus 1 is bigger than or equal to 2. Okay, and the next part is we need to show that it's less than 3. We have to show it's between 2 and 3. So how to show it's less than 3? Again, we go back to our inductive hypothesis, and you can actually do all of this in one step. But if you want to, you can break it up into these 2 steps. That's fine. So we go back to our inductive hypothesis that tells me that xk is less than 3. What I want to do is I want to build x square root. I want to build this square root xk plus 1. So if I square root both sides and I add 1 to both sides, what do I have here? This is xk plus 1. So xk plus 1 is less than root 3 plus 1. And if you plug this into your calculator, you'll get this to be a number less than 3. So from the second part, we know that xk plus 1 is less than 3. So therefore, xk plus 1 lies between 3 and 2, including the 2. And that's basically induction. So over there, you've shown that if the result holds for some natural number k, it's going to work for k plus 1. So it follows from induction that xn is bounded between 2 and 3. Okay, so this is bounded. Our sequence is bounded. And next part is to show whether or not it's increasing or decreasing. So if you want to just write down a few terms of the sequence, and you'll see that it's actually, the terms in it are actually getting larger and larger. So this sequence appears to be increasing. And what does that mean? That means that xn plus 1 is larger than xn. Okay, in other words, if it's increasing, x1 is going to be less than x2, and this is going to be less than x3, less than or equal to. Or if one, in this case, it's going to be strictly increasing. Okay, so the monotone convergence theorem also works for strictly increasing and strictly decreasing sequences. And we get that this is less than xn, and it's going to be less than xn plus 1. Okay, so what we're trying to prove is this part. Again, you need to use induction. So for n equal to 1, we need to figure out whether or not x2 is bigger than x1. So x2 is the square root of x1, which is 2, plus 1. And if you plug that into your calculator, you'll get this is bigger than 2. You don't need the number. All you need to know is whether or not it's bigger than 2. So x2 is bigger than x1. Okay, great. Next, we assume that our result is true for some k. And the next thing is we need to show that it's true for k plus 1. So if I substitute in k plus 1 for n, then I get xk plus 1 plus 1, right? Which is xk plus 2. And I need to show that this is bigger than, xk plus 1. This is what I need to show. So we consider xk plus 2. We know the formula for that. That's the square root of the guy before him. So that's k plus 1. Then we add 1 to it. But from our inductive hypothesis, we know that the square root of xk plus 1 is bigger than the square root of xk. Okay, so we could put that in over here. And this guy is equal to xk plus 1. So we get xk plus 2 is larger than xk plus 1. So the result follows by induction. So the inductive proofs is not very difficult, but you still need to write it out. So since xn is a bounded and increasing sequence, by the monotone convergence theorem, it converges. Okay, and in this case, if it's increasing, it's going to converge to the supremum of the range of the sequence. So let me just talk about that for a bit. Oh yeah, so we have the graphs over here. So if it's increasing and bounded, it's going to converge to this number here, right? You see the points. These are the terms in your sequence. They're increasing, but the sequence is bounded. So it's increasing to the sky. So our sequence was x1 equal 2, and xn plus 1 is the square root of the term before it plus 1. Okay, and we know that this sequence, all of the terms are bigger than or equal to 2 and it's less than 3. So, and we know it's increasing. Yeah, but it's bounded above by 3. So it can't get bigger than 3. But the question now is 3 the supremum of the range of Xn? Okay, because remember the monotone convergence theorem just tells us whether or not it's convergent. It doesn't tell you what it's convergent to. But we know from the proof and also from this, sort of diagram, we could see what's happening here, that if we have the range of the sequence, so if we were to write out all the possible values of the sequence, we would be able to figure out what the supremum is, and that would be what it's convergent to. So if we look at the range of the sequence, well, we know x1 is 2, then the guy after that is square root 2 plus 1, then the guy after that is the square root of square root 2 plus 1 plus 1, then the guy after that is, so you get the idea. You will have to work out these and you get a bunch of decimals. In other words, it's not very clear what the range of the sequence is. If I give you all a sequence xn equal 1 over n, then it's clear what the range of this sequence is. It's 1, a half, a third, a quarter, and so on. But for this sequence, we don't really know what the range is, so we don't have a good way of describing what the range is. There's actually a kind of easy way or easier way to work out what this guy is converging to. Okay, and for that, what we have to realize is that if this is a function that generates the term of your sequence, what you're putting in is xn, and this function is giving you xn plus 1. Okay, in other words, this function in our case is equal to square root xn plus 1. Okay, so think of this as being a machine. You throw in the term on the sequence and it produces for you the next term of your sequence. So if these terms are approaching some value, let's call it x. If they are approaching some value x, then when they reach to this value, if I throw in x, then the function should give me x coming out. Okay, because these terms are approaching this value. So in other words, these are what we call stationary points. Okay, the points where f of x is equal to x. These are what we call stationary points. When you put it in, you get it coming back out. So this is actually what we're looking for, a stationary point of this sequence. And all that means is, so you don't really need to know how to do this, but I'll tell you because it's useful to know. You take your sequence, right? And replace xn, because if the sequence is convergent, that means xn is going to x, and xn plus 1, well, that's just the next term. This should also be going to x. So all the terms should be going to x. So we replace xn plus 1 and xn by x. Okay, so we just replace it in this formula. And we will get x equals square root x plus 1. And this x in here, this is the limit. This is what we're trying to figure out. So if we, how do we want to do this? We could square both sides, I guess. So we get x squared. Actually, let me let me keep this guy on this side and put x minus 1 on the other side. Then let me square both sides. So I get x equal x minus 1 all squared, and that's equal to x squared minus 2x plus 1. And that's equal to x squared minus 3x plus 1 equals 0, I think. Yeah. Okay, and then you just need to solve this quadratic equation. So let's use the formula, quadratic formula. It's minus b, so that's minus 3 plus or minus square root b squared, that's 9 b squared minus 4ac, so that's just 4 all over 2 by a is 1. So it's 3 plus or minus the square root 5 all over 2. Okay, so you get 2 roots, but we know that this thing is that the if it's convergent, then the limit has to be unique. They can't have 2 values to the limit. So which one do we take? I think I suspect if you plug one of these values into a calculator, well, actually, we're just looking for the value. This is easier way to say. We're looking for the value between 2 and 3. Okay, because we know this sequence is bounded between 2 and 3. I suspect one of these is going to give you a negative number. So you could throw away that one. All right, so I think that this sequence is convergent to 3 plus root 5 over 2. Okay, so if you work out that in a calculator, yeah, you'll be able to get, yeah. This doesn't always work, okay? I should say that. It was easy in this case because the sequence we're dealing with is a nice, easy sequence to work with. However, with this next example, it's probably, I mean, we could do it for this next example, but it's going to be more difficult because now this sequence again is given to us by a recursive relation. We start at 2, but the n plus 1 term is a lot more complicated. It has even a second bit to it. Okay, and actually, as n goes to infinity, this second term, as n gets really, really big, what's happening to the second term? The denominator is blowing up. So if it's 1 over something that's getting very large, then this thing is getting very small. So as n goes to infinity, this guy here is actually going to 0. So that's just something to be aware of. Okay, again, we want to use monotone convergence theorem. So again, we will probably give you all a hint as to what is the bound for it. So they gave us a hint that the bound is between 2 and 4. So again, you need to use induction to prove this. So for the case of n equal 1, well, what is x1? x1 is 2. So 2 is clearly less than or equal to 2, which is clearly less than or equal to 4. So the result is true for n equal 1. That's our base case. Then we assume that it's true for some k. Okay. And now what we want to do is show that it holds for k plus 1. And what we could do is, well, we could write out xk plus 1, which is given to us. This is what xk plus 1 is from the formula. Okay. And I know that from my inductive hypothesis, xk is larger than or equal to 2. So I could say that this guy is bigger than or equal, and I could replace the xk over here. I could replace that by 2. And I also need a bound for this guy over here. Okay. What's a bound for this guy? Well, we know that k is a natural number, right? K is a natural number. Therefore, k plus 1 is always bigger than or equal to 2. K is a natural number, right? So k plus 1 is always bigger than or equal to 2. So if I do 1 over k plus 1, that's always less than or equal to 1 over 2. Okay, and if I do a minus on both sides, then I flip the sign. Okay, so we got a bound for this term. We have a bound for this term. So it's bigger than or equal to minus a half. Okay, so for these harder type of sequence, you sort of need to use a little bit of imagination to come up with these bounds. But all you need to do is to remember that the keys that you see in here are just natural numbers. So it's not too difficult to see k plus 1 is bigger than or equal to 2, right? If oh, we were searching for k cubed. Okay, yeah, well, if k plus 1 is bigger than or equal to 2, then certainly k cubed plus 1 is bigger than or equal to 2. It'll be the same thing, yeah. Right? K cubed plus 1 is bigger than or equal to 2. And again, you just flip both sides to get the k cubed plus 1 less than or equal to 2. You multiply it through by a minus sign and you flip here. Right? So it's not difficult to see how to build these things. All you need to do is remember that this k is a natural number. All right, so from this, we got, what did this first part give us? It gave us that xk plus 1 is larger than 2. So we got xk plus 1 is bigger than or equal to 2. Right? Bigger than or equal, or if you want, you could put xk plus 1 bigger than 2. Same thing. Same thing. Because if it's bigger than or equal to 2, it's certainly bigger than or equal to 2. Right? So this guy implies this guy. So we can write this. Okay, now we need to do the next bound. Now we need to bound it above by 4. So again, we write xk plus 1. Here he is. And we use our inductive hypothesis that tells me that xk is less than or equal to 4. Right? Xk is less than or equal to 4. So this xk over here, we could say that that's less than or equal to 4. Okay, because we could sub that guy in. Now we need to get a bound for this minus 1 over k cubed plus 1. Okay. But since we're looking for an upper bound for it, k is a natural number, right? So 1 over k cubed plus 1. I'll show you all how easy this is. I want to get a bound for, well, 1 over k cubed plus 1. This is a positive number because k is a natural number. This is a positive number. So minus it is, this is a negative number, right? And what do I want? I want an upper bound for it. Well, what's an upper bound for a negative number? 0. 0 is the upper bound for a negative number. Okay, so we could just replace this guy. We could say this guy is bigger than or equal to 0. Okay, so for this one, you didn't even need to construct anything. You just have to observe that if I want an upper bound for a negative number, I could put in a 0. And 0 is good to work with because it doesn't affect anything. Yeah. Right, and if I work out what this guy is on my calculator, I get that this is less than 4. So this next part gives me xk plus 1 is less than or equal to 4. Therefore, xk plus 1 is bounded between 4 and 2. Okay, so by induction, the result is true. Right, and so we show it's bounded. Now we need to show it's what? Increasing. So again, they gave us a little hint here that it's xn plus 1 is bigger than xn. So the n plus 1 term is bigger than the term before it. So it's increasing, right? This would be increasing. And again, if you didn't know this, all you have to do is just write out a few terms and see whether or not they're getting bigger or smaller. Okay, you can just write out the first 3 terms, and that should be enough. Okay, so is it true for n equal 1? Well, we need to check whether or not x2, which is given by this, is bigger than x1. x1, we were told, is equal to 2. So if you punch this into your calculator, you get a number bigger than 2. So the result is true when n is 1. Okay, let's assume that it's true for some k. Now we need to show that the result is true for k plus 1. Okay, so if we, for n equal k plus 1. So if we sub that into, remember we're substituting that into xn plus 1. So if we sub in for n, k plus 1, this gives xk plus 2. In case you're wondering why, if we need to show it's true for the case where n is equal to k plus 1, why are we considering xk plus 2? That's because when we take n equal to k plus 1 and we substitute it for n into our recursive formula, that's our recursive formula. This is our recursive formula. When we take n equal k plus 1 and sub it into here, this doesn't give me xk plus 1. This gives me xk plus 2. That's why we need to consider the k plus 2. Right? So we need to show k plus 2 is less than xk plus 1. That's what we need to show. All right. So what you do is you write out what is xk plus 2. Here's. Okay. And we need to use our inductive hypothesis somewhere. So we see xk plus 1. And I know that xk plus 1 is bigger than xk. So I could put a greater than sign here, and I could put him in here. Okay. So this guy is bigger than this guy. Now what we need to do is find a bound for the remaining piece, this term. What is this term bigger than? Well, I already know what I need to end up with over here because I know my aim is to get xk plus 1. So I know what this term is going to be. I just need to convince myself that this is true. So again, you need to sort of like sit down and do a little bit of trial and error calculation, kind of play around with it until you get it to work. And what we do here is we know that k plus 1, so this is how you could go about building that. This is bigger than k. Okay, k plus 1 is bigger than k. So k plus 1 cubed is bigger than k cubed. And if I add 1 across, right, k cubed plus 1, and then I flip both sides, this sign has to change, k cubed plus 1. But then I want minus this. So I put in a minus sign, and I flip back the sign. Okay, so you see we made an upper bound for it. Oh, sorry, we made a lower bound for it. So this guy is bigger than minus 1 over k cubed plus 1. All right, we knew what we had to end up with. We just needed to convince ourselves that it's true, right? And of course, this term now, this is simply xk plus 1. Okay, so we showed that xk plus 2 is bigger than xk plus 1. So the result follows by induction that it's increasing. So since my sequence is bounded and increasing by the monotone convergence theorem, it converges. Okay, so please make sure well, I know you have an exam coming up on Friday, so you're not going to touch this until after your exam. But for the following exam, your last coursework exam, please make sure you know how to do problems like this, simple problems like this, because most likely one of it is going to be on the third coursework exam. Right, I'll give you some some sequence. Most likely it's going to be with a recursive relation like what we just went through. I'll give you a hint what is bounded between, and I might tell you whether or not it's increasing or decreasing. If I don't tell you, then you have to figure that out on your own. Just write out the first 3 terms, see whether or not it's going up or down, and then use induction on it. Okay. And you have plenty of practice questions in the practice sheets and in the previous coursework exams. Okay, so make sure you can do this. All right. So what if, so this covers the case if we have a bounded increasing or a bounded decreasing. What if, so the monotone convergence theorem covers if it's bounded and either increasing or decreasing. Okay, it converges. What about the case if it's unbounded and increasing or decreasing? So this implies convergence. Then this implies divergence. Or I'll just put diverges. Okay, and that's given by this result. So if your sequence is unbounded and increasing, then the limit of it is equal to infinity. Okay, it just keeps getting big and big and big. Okay, so it's divergent to plus infinity. And if it's unbounded and decreasing, so it's blowing up but in the negative direction, then the limit of it is minus infinity. We say it diverges to minus infinity. Okay. All right, so this next definition is another important concept in analysis, is a very special type of sequence called a Cauchy sequence. Okay, so let me see if I can explain it and then we look at the definition. So when we were showing that any general sequence xn, if we wanted to show whether or not it's convergent, right, then we sort of need to have an idea as to what number it's convergent to. Okay, the monotone convergence theorem, yes, that's the way around it, but that only works for bounded monotone sequence. I'm talking about any general sequence. If I want to show any general sequence converges, I need to have an idea beforehand as to what it's convergent to, right? So I need to sort of try to figure out what it might be convergent to, and then I could go ahead and try to prove that. The idea of a Cauchy sequence is to eliminate all of this, is to somehow show a sequence is convergent without any knowledge of its limits. And so a Cauchy sequence is, I like to think of it like it's an almost convergent sequence. Okay, I like to think of it like it's almost convergent. And I'll explain to you what I mean. So let's talk about what a convergent sequence is. So here's the limit of this sequence, x. What a convergent sequence is, think of it like you're marching out. You're marching out. And these are the terms in my sequence. And as we march further out, these terms, they are getting closer and closer to this guy, which is the limit. Okay, this is the idea of a convergent sequence. As we march out further, all of the terms or each successive term is getting closer and closer to this limit. Okay, we're convergent to this guy. That's the limit. So this is a convergent sequence. Okay, let me draw for you what a Cauchy sequence is. Because a Cauchy sequence is very similar to it, but it has a very subtle difference. So a Cauchy sequence, I'm not even going to put a limit, because a Cauchy sequence, we will see when we look at the definition, there's no mention of a limit. Okay, there's no mention of a limit for a Cauchy sequence. So these are the terms of my sequence. As I march out, these terms are getting closer to each other. Okay. So you need to think of it this way. A convergent sequence, terms, I'll put here terms, are getting closer to a single value. And I'll put here, that's what we call the limits. So this is for a convergent sequence. For a Cauchy sequence, the terms are getting closer, not to a single value, to each other. Okay, so think of it like a long line, an infinitely long line of people. And as we're marching out, initially there's a big gap between everyone. But as we march out further, this gap between us is shrinking. Okay, and you might be thinking, okay, because how I drew it over here it appears that it is convergent. It appears that it should be convergent to something over here. Okay, and we'll talk about that. There's a strong link between Cauchy sequence and convergence sequence. Okay, but I want you all, if you're going to take away just 1 point from today's class, it's what's on your screen right now. That a convergent sequence means the terms are getting closer and closer to one specific number, one specific value, the limit. A Cauchy sequence means that the terms are getting closer and closer, not to a single value. There's no mention of no single value. They're getting closer and closer to each other. Okay, the terms, the distance between the terms is shrinking. Okay, and how do we measure distance again? Modulus. Right? So if xn is, let's say, this term, and xm is, let's say, that guy, the distance here is shrinking. The distance there is going to 0. All right, so let's look at the definition for a Cauchy sequence. Right? This is something you really need to have down for analysis because it's used so much. So a sequence of real numbers is said to be a Cauchy sequence. Sometimes we just use the word Cauchy, right? Usually mathematicians just say it's Cauchy. Okay, but we'll use the full term for now, said to be a Cauchy sequence. If for any epsilon, so for any radius, okay, so for any radius, there exists a natural number n. So it's looking like the same definition for a sequence so far. Okay, there exists a natural number n such that for n bigger than capital N, but look, I have another term here. I have an m now. Okay, for a Cauchy sequence, there's this next guy. There's an m as well. So I have 2 natural numbers, such that if I take 2 natural numbers bigger than this guy, the distance between these 2 terms is within epsilon. Okay, so let's say you give me epsilon equal to 1/2, and say I determine my n is equal to 12. What that means is if I take, let's say, n equal 15 and m equal 18, then the distance between the 15 term and the 18 term, again, it doesn't matter whether I do x15 minus x18 or x18 minus x15, because when you take the modulus is going to clear any negative sign anyway. So it doesn't matter which way around you do the difference. This distance is going to be less than that. That's what it means. Okay, so it's almost convergent, but not quite there. Right, so that's what a Cauchy sequence is. And of course, like I said, there's a strong relation between Cauchy sequence and convergence, which is given by the next lemma, that every convergent sequence is Cauchy. Okay, so convergent sequence implies your sequence is Cauchy. Okay, so every convergent sequence that you have met so far is also a Cauchy sequence. The proof of this, so suppose that our sequence is convergent, it converges to a point x, write the definition for the convergence. That means for any radius, there exists a natural number n, such that if I take a natural number k bigger than this n, the distance of that k term to this limit is less than epsilon, but to make things neat, we're going to do epsilon over 2. Okay, just to make things neat. So this is saying, remember, if I take any number bigger than this n, this works. Okay. So what if I, instead of taking one number, what if I take 2 numbers bigger than capital N? What if I take an m and an n bigger than this number? Okay, and what if I want to work on the distance between them? So what I could do in here is play this little trick where I add x and I subtract x. Okay, so I do this little trick where I add and subtract x, so I don't change anything. And then I use triangle inequality. Remember triangle inequality? Mod a plus b is less than or equal to mod a plus mod b. I use that. So this guy here is a, this guy here is b. Okay. So I get this term plus this term. But hey, m was bigger than n. So the distance between xm and x is less than epsilon, right? That's what this means. But now look, we also have something else. We have n is bigger than this capital N. So the distance between xn and x is less than epsilon. So when I add these two guys together, I get epsilon. So I get the distance between any two successive terms. Sorry, not successive terms, between any two terms, xm and xn, provided that they are bigger than capital N, is within epsilon, which is what Cauchy sequence is. Okay, so therefore xn is Cauchy, right? So please remember this convergence sequence imply Cauchy sequence. Okay, this always holds. So it's a big part of analysis to figure out when the converse holds. When does Cauchy sequence converge? And this next term over here basically says that if you're working in R, if your set is the real numbers, all of the real numbers, then Cauchy sequence always converge. So this is called Cauchy's convergence criterion. Okay, we already know that convergence imply Cauchy. We want to know, does a Cauchy sequence imply that it converges? This is what we want to know. Let me put the question over here. This term tells us yes. So it says that a sequence of real numbers is convergent if and only if it is Cauchy. Okay, if and only if. Well, we already proved this direction, right? We already proved this direction. This theorem is giving us the proof of the other direction. Okay, but it needs to be a sequence of real numbers. In other words, xn needs to be, xn is a sequence in R. Okay, it has to be a sequence in R for it to work. Okay. And this remark is saying from the Cauchy convergence criterion, we can show that a sequence of real numbers is convergent. So we can show it converges by simply showing that it is a Cauchy sequence. So this convergence criterion gives us another way of answering the question whether or not our sequence converges. Because in order to answer the question of whether any general sequence converges, we need to know or have an idea beforehand what it converges to. But if now I could show that my sequence is Cauchy, remember for a Cauchy sequence, there's no mention of any limit. Okay, if I could show my sequence is Cauchy, then by this theorem, it's also converges, and I don't even need to know the limit. Okay, so without needing to know the value of the limit. And we can also show that a sequence of real numbers is divergent by showing that it is not Cauchy. Okay, so remember this is an if and only if statement. So if your sequence is Cauchy, so I'll put is AUCHY is Cauchy implies is convergent, is not Cauchy. Because it's an if and only if statement, this means is not convergent. Okay, in other words, as long as we're in the real numbers, Cauchy sequences and convergence sequences are the same. Okay, they're equivalent. They're the same. The question now is, if we're not in the real numbers, so if we're in some other set, then does this still hold? Well, we know that convergence implies Cauchy always. Okay, this is always true. If we're not in the real numbers, does Cauchy imply convergence? If we're in the real numbers, the answer is yes. If we're not in the real numbers, the answer is not necessarily. Okay, there are many, many spaces where Cauchy sequences do not converge. Okay, and we have a special name for spaces for this. When I'll just put here, when Cauchy sequences implies convergent sequences, we say that space is complete. Okay, or sometimes we say it's a complete metric space. So if you ever come across the word complete or the metric space is complete, that's just a fancy way of saying that Cauchy sequences converge in that space. Okay, so it's a very nice type of space to work in, these complete metric spaces. And R, as you could probably tell, R is a complete metric space. Okay, R is complete. Cauchy sequences converge here. Okay, and that shouldn't come as a surprise based on my drawing here. Okay, because how I drew it for the Cauchy sequence part, these things, these terms, you could see they were getting closer and closer to each other, but that also means that they had to be getting closer and closer to a specific value. Okay, so, and the reason why this is true is because I was drawing this pertaining to the real numbers. So I was drawing this on the real number line. This blue horizontal line is the real number line. Okay, so it shouldn't have come as a surprise that this is the way that is. Of course, that drawing is not a proof, okay? The proof of this theorem, you don't have to know it. The proof is omitted. Okay, but the proof is a bit involved. You could always look it up if you want. Just search the name of the theorem and then see it. Okay, so let's look at an example of how to show sequences Cauchy. So say we're given this sequence, -1 to the n over n squared. So what do we do is we let epsilon be bigger than 0. And we need to choose a natural number such that n is larger than, like I said, when you do any proof for the first time, you don't know what this is. So you leave it blank, and then fill it out after. Okay, so just put choose a n such that, then if we take m and n bigger than this n, where m and n are natural numbers, we need to evaluate what is this distance. Okay, so xm and xn, well, we have the formula for it. Here they gave us the formula. So all I do is I just use that formula over here. So this is xm and this is xn. So I just use the formula. Then I use triangle inequality again. So again, that's mod A plus B is less than or equal to mod A plus mod B. Okay, so this guy is A and this guy is B. And notice that so I'll do, for example, the modulus of -1 to the m all over m squared, that's equal, I'll put the next rule here, mod A over B is equal to modulus of A divided by modulus of B. Okay, so that's equal to the modulus of -1 to the m over modulus of m squared. That's equal, what is the modulus of -1 to the m? So this number is either +1 or -1, but the modulus gets rid of any minus sign. So what comes out of here is always +1. Okay, so the modulus of -1 to any power is always 1. Just remember that. And m squared, well, m is a natural number, so even if you square it, it's going to be positive. So that's the same thing. Okay, so that's how they got 1 over m squared over here. Right, and in a similar way, we get 1 over n squared for this guy. All right. But what do we know about m? We know m is larger than n. Okay, so therefore, if I square both sides, I get m squared is larger than n squared. So 1 over m squared is less than 1 over n squared. And in a similar way, 1 over n squared is less than 1 over capital N squared. So this guy is less than 1 over n squared, and this guy is less than 1 over n squared. When I add them together, I get 2n squared. And this here is a constant. Okay, so we set this constant less than epsilon. So from all of that, we get epsilon is bigger than 2 over n squared, solve for n squared. Oh, sorry, solve for n. Right? So that's n. N is bigger than square root 2 on epsilon. And you take that and you put it over here. That's where they got it from. Okay. So from here, and this is a Cauchy sequence. So, and we didn't even know what the limit of the sequence is. So by the Cauchy convergence criterion, it converges. Okay, so I'll leave you all to read through the second example. Okay. So we have some exercises here. Make sure and try these. I have the solution for all of this, I think, up already. Right, so try them before you look at the solutions. Then look at it. Okay, so subsequences. Let's talk about this. So what a subsequence is pretty much what the name sounds like. You have a sequence and you just pull out a bunch of terms from it and you form a new sequence, a subsequence. Okay, so let xn be some sequence. So xn, x1, x2, x3, x4, and so on, right? Then we have another sequence, nk. Okay, this sequence is a sequence of natural numbers. So it's a sequence of natural numbers such that the first term is less than the second term is less than the third term, and so on. So it's an increasing, strictly increasing sequence of natural numbers. So I'll give you an example of what this might be. This might be like 2, 5, 7, 11, 12, 13, something like that, right? So it's each term it's a strictly increasing sequence of natural numbers. Now you might be wondering, what is this sequence I just wrote? This sequence, think of it like an index sequence. This sequence tells us which term of the original sequence to pick out. So it's telling me pick out the second term, the fifth term, the seventh term, the 11th term, and so on from my original sequence and form a new sequence with it. Okay, so the sequence x sub nk, so it's a subscript on a subscript. This is what is called a subsequence of xn. And in this case, it will be something like x2, x5. So you see, it's telling me what the terms are over here. x2, x5, x7, x11, x12, x13, and so on. So it basically tells you which term of your original sequence to take. Okay. But you don't even need to know what this index sequence is about to know what was a subsequence, right? If I give you an initial sequence, just pull out a bunch of terms from it and form a new sequence with that. That's a subsequence. So for example, if your sequence xn is 1 over root n, so let's write out a couple terms of this sequence. So it's 1, 1 over root 2, 1 over root 3, 1 over root 4, and so on, right? If I take as my index nk to be 2k, so what are these terms? K is a natural number, so k runs from 1 to infinity. So this is 2, 4, 6, 8, 10, 12. What terms are these? These are the even terms, right? So the sequence x and k is telling me to choose out all the even terms over here. So it's choosing out the second term, not even in terms of what the of what the value of the term is, even in terms of the position of it. So it's telling me choose out the second term, the fourth term, the sixth term, the eighth term, and so on, right? And if you want to see how that looks like, we'll just do x n k. Well, what is n? N is 2 times k. So you take 2 times k and sub it in for n, and you get 1 over root 2k. Okay, and that would generate for you 1 over root 2, 1 over root 4, 1 over root 2, 1 over root 4, 1 over root 6. It would generate for you the sequence. Okay, so it's a clever way of doing something that we already know how to do. And if, for example, we do mk to be 4 to the power of k, then this is going to pick out the fourth term, this will pick out the fourth term, the 4 squared, which is 16, the 4 cubed. So 16 times 4 is what? 64, maybe. And then whatever is 4 to the power of 4 and so on. Okay, 108 or something. Oh, sorry, not 108. 128, 132. Anyway, you can work it out. So that's what this other sequence is picking out, right? So all of these are subsequent. And if you have a sequence now, so let's do another example. The sequence 2n, where n is a natural number, so this is just 2, 4, 6, 8, 10, 12. It's the positive even numbers. And 2 to the n minus 1, that's just, these are just the odd numbers. So let me call this the even, and let me call this the odd. Okay. And 3 times n, these are just multiples of 3. Okay. So all of these are subsequence of this guy, n. What is the sequence n? So again, we could write it like this, or you could write it like this. It doesn't matter. Or you could write it as, it doesn't matter. What is the sequence? This is just 1, 2, 3, 4, 5, 6, and so on, right? So if we pick out all the even terms, we get this guy. If we pick out all the odd terms, we get this guy. If we pick out all the multiples of 3, we get this guy. Okay, so one sequence can have so many subsequences. Okay, it all depends on, you know, what are the terms you want to pick out. So what makes these subsequence so important? Okay, so we have this cute lemma over here that says for this index sequence nk, so if this is an increase in sequence of natural numbers, such that, well, nk is less than nk plus 1. That means it's strictly increasing. So it's a strictly increasing sequence of natural numbers. Then nk is always larger than or equal to k. Okay, what does that mean? Let me give you an example. What's a strictly increasing sequence of natural numbers? 10, let's go 25, 26, 27, and so on. Okay, so this is nk. K is the term. So this is the first term, second term, third term, fourth term, fifth term, sixth term, and so on. They are saying that nk is always bigger than or equal to this guy. Okay, so you see it roots out. It's always bigger than or equal to this guy. The proof of this, I'll leave you all to go through the proof. The proof very easy is by induction, right? But it's something nice to know. This kind of comes in handy later on in other courses. Nk is bigger than or equal to k. And where you need it was for this theorem that says if a sequence converges to x, okay, if xn converges to x, where x is a real number, then every subsequence of this guy, so we just looked at how to form these subsequence, every subsequence is also going to converge to x. Okay, so it's a very important theorem. It's saying if your sequence converges to some value, if you take any subsequence of x, it's also going to converge to x. All of them are going to basically converge to x. Right? I'll leave you all to go through the proof. Here's not a difficult proof to go through. It uses the lemma above. So that proof you can read later. What's useful from this theorem is we could actually use this to tell whether or not a sequence diverges. That's given by this remark. We can use this theorem to show that a sequence is divergent by finding any two subsequence that converges to different limits. Okay, because we know that if the original sequence converges to x, then all the subsequences of it must also converge to x. So if you could find a sequence, and we don't know whether or not this sequence is convergent, right? We don't know whether it's convergent. If we could find a subsequence that converges, let's say to x1, let me not use x1, that converges to L1, and the next guy that converges to L2, and these are not the same, then there's no way xn is convergent to any value. Okay, because if it was convergent, then all the subsequents would be convergent to the same. So it gives us a very clever way to tell or to check if a sequence could be divergent. Let's look at an example. The best cases for that are alternating sequence. Okay, so this guy, this was one of the first sequence we met, and we went through how to, well, we didn't go through, but the proof was there on how to show using the epsilon definition for convergence of a sequence. Kind of messy, kind of tricky how to do. It was how to show that this thing diverges. But let's show how it diverges using this method. And you'll see it's so much easier. What is the sequence? It's -1 to the n. So it's, how does it go? It goes -1, 1, -1, 1, -1, 1, -1, 1, right? So that's the sequence, and it keeps going. If I pull out a subsequence of all the odd terms, so the first term, the third term, the fifth term, the seventh term, and so on, then all of these are what? These are -1s. So this guy converges to -1. Okay, great. If I pull out a sequence of all the even terms, so the second term, the fourth term, the sixth term, the eighth term, and so on, what is the sequence? What are these terms? These are just ones. So they're going to converge to one. So I have two subsequents, one convergent to one and the other one convergent to -1. So there's no way the sequence is convergent. Okay, so they have to write up for it over here. If we take x2n and x2n plus 1, this is the one for the even terms, and this is the one for the odd terms. Okay, it's two subsequences that converge to 1 and -1 respectively. So therefore, the original guy cannot converge. And we have Bolzano-Weierstrass theorem for sequences. So we met this guy in what chapter? The one for limits, I think. Right? Bolzano-Weierstrass theorem. Every bounded infinite subset of R has a limit point. Well, this is what it is in the language of sequence. Okay, we don't need to know how to prove it. Although you all could prove this. You all have everything you need to prove it. To prove it, you need to use Bolzano-Weierstrass theorem, the original one, to prove this. And it basically says every bounded sequence has a convergent subsequence. Okay, so if a sequence is bounded, it doesn't matter. So if we know if xn is bounded, then does this imply that it converge? No. Bounded does not imply it converge. Look, we just spoke about a bounded sequence here. That doesn't converge. So bounded doesn't imply converge. But what this is saying is that if your sequence is bounded, then it has or there exists a convergent subsequence. Okay, so you can find a subsequence of it that converges simply because it's bounded. Okay, so you have some more examples here. I'll leave you all to go through this. Okay, these are just some more examples on how to show whether or not oscillating sequences diverge. Basically, what you're trying to do is you're trying to find hidden within this sequence, you're trying to find two subsequences that converge to two different values. Okay, and one of them is a sine function. So you should know that sine is periodic so that eventually the values are going to start repeating. So I think this well, you'll see when you go through it that basically this sequence here, the range of this is finite. It only has like a finite number of values. So maybe every 10 values, this thing starts repeating itself. So what you could do is you could just take out every 10th value and form one sequence, and then let's say every 11th value and form another sequence that converges to two different values. So what they did was they formed one sequence that's convergent to 0, and they formed another sequence that's convergent to 1. Okay, so this guy doesn't converge. So you could go through that. And the last thing we need to talk about is something called sequential compactness. So we met with compactment and I think it was chapter 3 when we were talking about topological properties of numbers. That is the whole every open cover has finite subcover. And we came across Heine-Borel that tells us A, which is a subset of R, is compact. Make sure you know this, okay? This is very important. If and only if it is closed and bounded. Okay, that was Heine-Borel. So what we're going to talk about now is how to translate the idea of compactness to the language of sequence. So we say a set A, which is a subset of R, is said to be sequentially compact. Okay, sequentially compact. If every sequence in A has a convergent subsequence whose limit also belongs in E. Okay, the limit must also belong in E. So for example, let's look at some examples. The open interval 0, 1. This is not sequentially compact. Why is it not sequentially compact? Because I could find a sequence. Here is 1 over n plus 1 in the set. So all the terms of the sequence belong to the set. If you don't believe me, let's write it out. A half, a third, a quarter, a fifth, sixth, and so on. So all of these terms belong to open interval 0, 1. So it's a sequence in the set. However, this sequence is convergent to what? To 0. 0 is not in the set. Okay, so this sequence is convergent to a value that's not in the set. It's convergent to 0. So that means, well, if the original sequence converges to 0, remember we just looked at the term that says every subsequence of it must also converge to 0. So if x and k is any subsequence, it must also converge to 0. So what we have done is we have found the sequence in the set such that every subsequence also converges to a point not in the set. So therefore, this sequence has no convergent subsequence whose limit belongs to the set. Okay? The key part is this. The limit of it has to belong to the set because the limit exists, it's 0. The problem is 0 is not in the set. Okay, so this set is not sequentially compact. Sequentially compact, all of the limits of the subsequence have to belong to the set. Okay, so if every sequence has a convergent subsequence whose limit belongs to the set. Right. So make sure you know this one as well. This is very important. Let's look at another example. So this guy, not sequentially compact. Is this set compact, by the way? COMPCT. That is not compact, right? So I'll put over here because behind in Borel it's bounded, but it's not closed. It's an open interval. So I'll put over here not compact as well. Okay, so it's not compact and not sequentially compact. Let's go on to the next one. If A is the set, all the rational numbers such that their square is less than √2. So another way we could write this is simply all the rational numbers between plus and minus √2, where x belongs to q. Okay, it's just all the rational numbers between plus and minus √2. Right. So is this set sequentially compact? Well, we know from the density of the rational numbers in R, remember that means you could always find a rational between any irrationals. We can find a sequence Rn in A that converges to square root 2. Okay, why is this so? Because remember that the derived set of Q of the rational numbers, the set of all limit points of this size R. Okay, so every real number is a limit point of Q. Okay, every real number is a limit point of Q. That means, and what do we know about limit points? If x is a limit point of density of the rational, if f, sorry, it should be q, what I want it to be is qc. right? And y to be a limit point of the irrational numbers. So if x, which is still r, so if x is the limit point of QC of the irrational numbers, then there exists a sequence that converges to x. So there exists a sequence of irrational numbers that converge to x. And also, since already next case, since q prime is equal to r, then if x is a limit point of q, there exists a sequence in q, so a sequence of rational numbers that converges to x. So this is what they're using. Okay, they're saying the fact that square root 2, which is an irrational number, okay, so they're saying since this is a limit point of since this is a real number and every real number is a limit point of the rational numbers, there exists a sequence of rational numbers that converges to it. There exists a sequence of rational numbers that converges to it. Okay, so actually, let me write something over here in case I confuse you with all of that. Let x be any real number, then there exists a sequence of both rationals and irrationals that converges to x. Okay, if you take any real number, I could always construct a sequence of rational numbers that converge to it, or I could always construct a sequence of irrational numbers that converge to it. That's actually how the real numbers was created. Okay, it was created to have this sort of thing. Anyway, so square root 2 is a real number. We could always find a sequence of rational numbers in A that converge to it. Okay, sequence of rational numbers in A that converge to it. Every subsequence of this will also converge to square root 2. Okay, because if a sequence converges to some number, all the subsequence is going to converge to that same number. So all the subsequence of this guy will converge to root 2. The problem is root 2 is not in the set. Okay, so this sequence will have no subsequence that converges in A. So A is not compact. Right? A in this case, again, is not compact. So we could kind of use this stuff mainly to show when a set is not, not sequentially compact. Yeah, here's a typo. It should be A is not sequentially compact. We'll see in a bit that doesn't matter for now. Okay, so this set is not sequentially compact. Is this set compact? It's certainly bounded, right? It's bounded between root 2 and minus root 2. But this set is actually not closed. It doesn't contain all its limit points. Okay, for example, square root 2 is a limit point, but it doesn't contain root 2. So it's not closed. So tiny corral, it's not compact, not sequential. So we start to see a trend here. Not compact means not sequential. Right. Let's look at the last one, for example. So the sequence n, which is just 1, 2, 3, 4, 5, and so on. This sequence has no convergent subsequence. Okay, because any subsequence you take for this is going to be increasing, strictly increasing, and is going to converge to, well, it's going to diverge to infinity. Okay, So this sequence has no convergent subsequence since every subsequence diverges to infinity. So n is not, again, it should be not sequentially compact, not, n is not sequentially compact. Is n compact? N is closed, but n is not bounded. It's not bounded above. So like Heine-Borel, n is not compact. Okay, so we're seeing a link here. Sets which are not sequentially compact are also not compact. And it should be no surprise because of the name that they chose to describe this property, compact, sequentially compact. Actually, for R, or for these sort of spaces, which are called metric spaces, sequentially compact is equivalent to compact. They mean the same thing. Okay, and that's given by this term over here. A subset of R is sequentially compact if and only if it is closed and bounded. Closed and bounded, subset of R. What is that? What does Heine-Borel tell us? Heine-Borel tells us this is the same thing as compact. Okay, sequentially compact is the same thing as compact. It's just another way of measuring it. Okay, and we have this corollary: a subset of R is sequentially compact if and only if it is compact. And the proof of this follows directly from Heine-Borel. Yeah, so if you want to determine whether or not a set is sequentially compact, you can either go from the definition that says that every sequence in that set has at least one convergent subsequence whose limit is also in that set. Okay, if you could show that there's a sequence in that set that has no subsequence whose limit belong in that set, then it cannot be sequentially compact. So sequentially compact is kind of, it is not too difficult to wrap your head around it, but it takes some time. It takes some time reading over this definition and sort of trying to torture it in your mind. But close and bounded is something we're familiar with at this point. So another way to identify sequentially compact is just check Heine-Borel and see whether or not it's compact. So let's do that. This interval, closed interval AB, is closed and bounded. So by Heine-Borel, it's compact. So it's sequentially compact. These sets N, V, Q, R, they're closed. Sorry, Q is not closed, but they are all unbounded. So by Heine-Borel, they are not compact, which means they are not sequentially compact. This half-open interval is closed, but it's not bounded. Okay, it's not bounded above. So Heine-Borel tells me this is not compact, hence it's not sequentially compact. This interval, okay, sorry, not interval. This set 1 over n, so it contains 1, a half, a third, a quarter, and so on, right? It's bounded, okay, but it's not closed. Why is it not closed? Because 0 is a limit point of this set, but 0 isn't in this set. Okay, remember, for a set to be closed, the derived set must be contained inside of E. Or said another way, the closure must be equal to E. Okay, so hopefully this isn't unfamiliar to you. So this that is not closed, so by Heine Borel, it's not compact, so it's not sequentially compact. However, if I add 0 into the set, so that now it is closed and bounded, Heine Borel tells me closed and bounded is compact, therefore it is now sequentially compact. Okay, so if A is a subset of R, sequentially compact is the same thing as closed and bounded is the same thing as compact, right? Make sure you know this. This way is Heine Borel. Probably spell that wrong. B-O-R-E. H-E-N-I. Heine. H-E-I-N. Yeah, I think that one is it. Heine Borel. And this other one is, what is it? Theorem 5.4.3. Okay, so you can move back and forth between them as long as you're in, as long as you're a subset of them. Okay. Okay, so that's it for this chapter. Um, so we'll call it there for today. And, so Friday is the exam. So I'll see you all on Monday then. Next week we'll wrap up the last chapter, which is sequence. Oh, sorry, series. This was sequence. So we just need to do series. Okay, which shouldn't take too long. That'll be it. Any questions?